In this video, we're going to prove the following fact. There is no non-abelian simple group of order 90. If you like watching mathematical proofs, you should consider subscribing to my channel, as that's what we do here. Let's get into the proof. By way of contradiction, let's assume the following. Assume that G is non-abelian, simple, and that the order of G is 90. Okay, so let's use some Sylow theorems and let's see what's going on here. So 90 is 10 times 9. Well, that's 9, and 10 is 2 times 5. So we're guaranteed to have at least one Sylow 2 subgroups of order 2, at least one Sylow 3 subgroup of order 9, 3 squared is 9, and at least one Sylow 5 subgroup of order 5. So let's see what the possibilities are. Well, we know that N2, which is a number, are Sylow 2 subgroups, so we may be beneficial to write this down, say, 3 times. Now, when it comes to what N2 divides, it has to be whichever left over after we cross out 2 to some power, in our case 2 to 1. And what's left over is the number 45. That implies that N must be 1 or 3 or 5, 9, 15, or 45. That's one constraint. The other constraint is N2 must be congruent to 1 mod that number. Well, 1 mod 2, that means after dividing by 2 you get a remainder of 1. This just implies that N2 is odd. Well, all of those numbers are odd. So N2 is in the set 1, 3, 5, 9, 15, and 45. But for N to be simple, you don't want 1. Okay. So now we have that. Oh, so yeah, all of these numbers are odd. So that one's done. Now, let us look at N3. It must divide 90 without the 3 squared. That is, it must divide 10. Well, the only numbers, positive integers I know of that divide 10 are 1, 2, 5, and 10. And again, we don't want to use 1. And N3 must also be congruent to 1 mod 3. That is, it's 1 more than numbers on the 3 times table. Numbers on the 3 times table are 0, 3, 6, 9, and ours are going to be 1 more. And if you note, and we're not going to have 1. And if you notice, the only numbers in common is one single number, and that number is 10. Both of these sets have 10. So N3 we know is exactly 10. Now let's consider N5. Well, N5, it must divide that product not including 5. And if it was 5 to a power, we wouldn't include that power. It's just 2 times 9, or 18. All the numbers that divide 18 without using 1 are 2, 3, 6, 9, and 18. And we want N5 to be one more than numbers on the 5 table. Well, that implies that N5 contains 1, 6, 11, 16, 21. And again, we're not including 1. Oh, look at that. The only number in both is 6. So N5 is 6. Okay. N5 is 6. So now, let's look at, I just want to have this in front of me. 2 times 3 squared times 5. So, let us look at N5. The number of Sylow 5 subgroups is 6. So N5 equals 6. That implies that there exists 6 Sylow 5 subgroups, all of order 5. Okay. These 6 Sylow 5 subgroups all have to be disjoint, other than having the common identity element in both. That is, these six Sylow subgroups, they give us 6 times, well, each subgroup has 5, one of which is always their identity. If we pull out the identity, that means these 6 Sylow 5 subgroups contribute 24 non-identity disjoint elements over G. So far, we found 24 non-identity elements in G. And just want to use a different word here. Disjoint. They have none in common, these 24. Okay, subgroups are all distinct, and we have 6 distinct Sylow 5 subgroups, except for the identity element. Once you have another element, forget about it. It's because of the order being 5. Now we have that. Let's look at n sub 2. So n sub 2, let's pick the smallest one. You know what? Let's not even consider n2. Let's go right to n3. That should be enough to finish the problem, I bet. n3 equaling 10. That implies that there exists 10 Sylow 3 subgroups, all of order 3 squared, 9. Okay. Let their subgroups be, let their 10 subgroups be P1, P2, up to P10. Now, we have 2 cases to consider. Case 1. Pi intersect Pj is always the identity no matter what two I consider. Okay, so what does this tell us? Well, what we know then is that, let's see, each Sylow 3 group has 9 elements, only one of which is the identity element. That is, there's 8 non-identity elements, and we have 10 of them. This gives us 80 non-identity elements from G. Okay, now in n sub 5, the order of each element is 5. In these Sylow 3 subgroups, the order of each element is 3 or 9. Well, if you're an element of 5, you're not an element of 3, nor are you an element of 9. Likewise, if you're an element of 3, if you're an element, yes, of order 3 or 9, you're not an element of order 5. That is, these 24 non-identity elements and these 80 non-identity elements, they have nothing in common. Okay, so putting this together, we have 80 plus 24, 24 and 80 plus 1, which is equal to 125. Where did the 1 come from? It's the identity element, just in case we need it. Elements from G. But the order of G is 90. The order of G is 90. Let me not say it 90 is less than. Let me say 125 is bigger than 90. We have too many elements in G. So case number 1 cannot happen. Okay, let us consider case number 2. This says that Pi, not everyone, but this says there exists I and J, I not equal to J, such that Pi intersect Pj is not the identity element. Okay, well, first thing I would think of is then there exists an x not equal to E that lies in the intersection. Okay. Now let's consider the class, or the centralizer of x. Well, this is equal to the set of all x and g's, the set of all little g's in the group G that commute with x. That's the definition for the centralizer of x in G. Okay. Now, clearly x is in there. Clearly x is in this set, because x certainly commutes with x. This x is that x, this x is that x, they commute. So we know it has at least one element. Okay. let's actually say that in case we need it. Well, let's say it here. This implies that x is in the centralizer of x. Okay. Now, the order, well, before we talk about order, the centralizer of x is a subgroup of G. This implies that the centralizer of x divides the order of G, which is 90. The centralizer of G divides the order of G. It divides 90. Okay. Let's see now. What do we know? Okay, so now let's talk about the order of PI intersect PJ. We know that this is a subgroup of PI, and for the record, and PJ. So this means that the order of PI intersect PJ must divide the order of PI, but the order of PI is 9. Because let's be 100% right, these PIs are Sylow 3 subgroups of order 9. Okay. So, this implies that the order of PI intersects 3PJ is in the set of all divisors of 9, which is 1, 3, and 9. Now, if the order is 1, that implies that PI intersect PJ is not the set that just is the set that just contains E. But that's a contradiction. We said that X is in this set and X is not E. Okay, so it can't be 1. Now let's argue 9. Why it can't be 9. If this is equal to 9, well, each of these elements have 9 elements. Each of these sets have 9 elements, and if their intersection has 9 elements, that implies that PI equals PJ. But let's come up here for a moment. The 10 Sylow subgroups, P1 through P10, I'm assuming they're different. No two are the same. Otherwise, the number of Sylow 3 subgroups equaling 10 would really mean the number of Sylow 3 subgroups is less than or equal to 10. These are 10 different Sylow 3 subgroups, all of order 9. Okay, so that's a contradiction. So, we can't, the order of PI intersect PJ can't be 9, it can't be 1, must be 3. So, the order of PI intersect PJ is 3. Okay, wonderful. Now, since the order of PI is equal to the order of PJ, which is 9, which is 3 squared, that means a prime squared. That implies that PI and PJ are abelian. Okay. Now, I claim that X commutes with all elements ELTS, all elements in PI and PJ. Commute with all elements from PI and PJ. Pretty simple. Well, that's actually not what I want to say. I want to say it commutes with their product. Okay, so how about we let P sub I, little p sub I, little p sub j be in big PI, PJ, where PI is in PI and little pj is in big PJ. Okay, now here's an arbitrary element in here, and I want to show that x commutes with it. So x times PI, PJ, we could use the associative law. Each of these three elements are in G. So I can say this, and PI commutes with is abelian, and x is in PI. X is in PI intersect PJ, so x is in both PI and PJ. Okay, so this I can write as PIX times PJ, associative law again. Now x is in the intersection of PI and PJ. In particular, x is in PJ. But elements in PJ commute. So we get PI times PJ times x. And one more associative law. We get PI times PJ times x. So look at this element commutes with x. Okay, so this implies that every element in PI, PJ is in the centralizer of x, is in CG of x, the centralizer of x. Why? Because every one of these elements, every one of the elements in here commute with x. How many elements are in there? Well, PI, PJ, the order of that is equal to the order of PI times the order of PJ divided by the order of the intersection. Well, the order of PI is 9, the order of PJ is 9, and the order of PI intersect PJ, I'm pretty sure we argued was 3. There it is, even in red. Okay, so this gives me 27 elements. And these 27 elements is in the centralizer of x. So the centralizer of x, the order is at least 27. So we have the centralizer has at least 27 elements. And I hope there was one other place. And the centralizer must divide 90. Now let me put this here. The centralizer of x, the order, must divide 90. The centralizer of x must be at least 27. And P sub I is a subgroup of the centralizer of x. This implies that the centralizer of x, well, this implies this divides that, and this is of order 9. So let's actually say that. So this implies that the order of pi, which is 9, divides the order of the centralizer. Well, the only way p sub I divides the order of the centralizer, that is the only way that 9 divides the order of the centralizer, is if the order of the centralizer is a multiple of 9. Okay, so we have a few things. They're all in red right in front of us. 1, 2, and 3. They'd all talk about the order of the centralizer. It's at least 27. Okay, and it divides 90. Well, let's see the numbers that divide 90. 1 and 90, 2 and 45, 3 and 30, 5 and 18, 6 and 15, 8, 9, and 10. These are all the numbers of positive integers that divide 90. And I'm going to cross off all of these for one simple reason. They're not bigger than or equal to 27. Okay, so far, before I crossed off those numbers, I just wrote down the numbers that satisfy number 2. You have to satisfy 1, 2, and 3. So I crossed off these numbers because they didn't satisfy condition 1. And the third condition is they have to be multiple of 9. 30 is not a multiple of 9. So, this is kind of side work, I guess. So since I numbered them, 1, 2, and 3 implies that the order of the centralizer is either 45 or 90. Let's write it in set notation. It's either 45 or 90. Okay. Now, if the centralizer of x, the order is equal to 45, has 45 elements, and the 45 elements go into the order of the group, which is 92 times. That implies that the index of G with the centralizer of x equals 2. But that implies that the centralizer of x is normal in G by the index 2 rule. Whenever the indexes of a subgroup is 2, then that subgroup is normal in G. Okay, so this is normal in G. Okay. But let's say this carefully. The order of the centralizer is bigger than 1. I know that because it's at least 27, and right now we're saying that it's 45, which is less than 90. But that would imply that G is not simple. That's a contradiction. Okay? We're assuming that, let us look at it. We're assuming that G is simple. And remember, I want to get a contradiction. Okay, so G is not simple. Okay, but nonetheless, that contradicted what I assumed. Okay, so suppose that the centralizer of x is equal to 90. Well, that would imply, so this means that x commutes with 90 elements of G. But that's all of G. X commutes with every element in G. Well, that implies that x is in the center of G. X is in the center of G. But that can't be. Let's see why. Let us see why. So right now we're talking about a particular case. We're talking about Sylow's three subgroups. Sylow's three subgroups. Okay? And I proved it in one or two videos in the back. Okay. We know that if a group is a P group, then the center is not equal to 1. That is, the center is not trivial. Okay, I was thinking about this last statement I wrote, and that's not true. Okay. So we found a non-identity element in Z of G. Okay. So that implies that Z of G is not the empty set. Now, if the order of Z is 90, that would imply that G is abelian. But that's a contradiction. We're assumed from the very beginning that G is not abelian. So the order of the center is bigger than 1, but it's less than 90, which is the order of the group. But there's a problem here. For since the center of a group is always normal in the group, we have that G is not simple. I found a normal subgroup of G happened to be the center, but nonetheless I found a normal subgroup that wasn't equal to the identity, and it's not equal to the entire group. That means we found that G is not simple, and that is a contradiction, and that completes this proof. Okay, what we showed is that there is no way that G is non-abelian simple. Okay, that doesn't happen. If you like watching mathematical proofs like this, consider subscribing to my channel. Please leave a comment, click the like button. Once again, subscribe Tell your family and friends about my channel. I'm sure that your enemies will really love watching my advanced math videos. Don't forget, watch and learn.